Hello everyone, how's it going? My name is Dan the Tutor. In today's video, we're going to be talking about friction. Friction comes into play with forces, usually not at the beginning. Usually we like to do a few easier problems without friction with forces, and then we move on to the harder ones that will have friction. So here's everything you need to know about friction. There's two kinds of friction. Well, technically there's like four kinds, but the only two you need to know for this class are static friction and kinetic friction. And what I'm going to do for us is I'm going to make a Venn diagram of these two things. So number one, the most obvious thing, static friction is when an object is not moving, and kinetic friction is when an object is moving. The simplest example of this is if you try and push a couch and you don't push hard enough so it's not moving, that's static friction. But let's say you're pushing on something lighter, like a book, and you push that book across the table, well, now that's kinetic friction because we're moving the object. Static friction and kinetic friction do have different equations. I like to say for static, Fs, static friction force, is less than or equal to mu s times the normal force Fn. Now I have to explain what the coefficient of friction is. So this symbol right here, mu, Greek letter mu, mu, stands for coefficient of friction. And it basically describes how rough or how smooth a surface is. Higher coefficient of friction, more friction. Lower coefficient of friction, that means it's more slippery, like ice. And usually the coefficient of friction is between 0 and 1. For instance, 0.2, 0.8, 0.5, whatever. Technically, the coefficient of friction can be greater than 1, but you usually don't see examples of that. And it cannot be less than 0. You cannot have a negative coefficient of friction. Usually this is a value they give you in the problem or you're solving for it. And the last thing I need to say about this equation for static friction less than or equal to mu s times normal force, the reason why it's less than or equal to is because it's not the same every time. For instance, if I try and push the bookshelf next to me with 10 newtons of force and it's not moving, then that means the static friction force is 10 newtons. But let's say I try pushing harder, like 20 newtons, still not moving, so it's still static. Well, then the static friction force is now 20 newtons. Meaning, the static friction is kind of like a magical force in the sense that however hard I push on it, seemingly out of nowhere, the static friction force is going to equal and match my force, canceling it out. The only time it doesn't cancel out is when we're moving, and then we're in the kinetic region where the equation is Fk is equal to mu k times the normal force. So since Fk has an equal sign, that means you can actually use this equation to solve. With the static friction force, you're not going to be using this equation unless we're talking about the max static friction. In that case, that is the only time you get to say it's equal to. And when I say max, I'm saying if you push any harder, we're starting to move. That's the only time static friction force equals coefficient times normal force. Now, for that reason, 90% of problems using static friction is going to use this equation right here, looking at the max. And we'll look at some example problems in later videos discussing more specifically what that means. But there is one thing they both have in common. Both static and kinetic friction always oppose motion. Meaning if you want to push an object to the right, friction's always going to point to the left. It always opposes motion. So that's it for the Venn diagram. The only other thing I want to show today is a little graph that displays how friction works. So on the x-axis, let's say this is my applied force, in other words, how hard I'm pushing on the object or pulling on the object. And on the y-axis, we have the force of friction. Now, for very small values of the force, we're not going to move the object. And the graph is going to look like this. It's linear. And this right here is the static region. We're not moving because you didn't push hard enough yet. But at this point right here, where we get to Fs max, the max static friction force, that's when we're going to move over to the kinetic region. And the kinetic region looks like a flat line, or at least that's supposed to be flat, and it is lower than the static friction force. So what this means in real life, and maybe you've experienced this firsthand, if you are trying to move something really heavy like a couch, it's actually easier to push the couch once it's already moving. It's harder to get it started, but once you get it started, it's actually easier to push. And you can even test that for yourself if you really want to. And so just as a quick reminder, this part in red has basically no equation, because if its Fs is less than or equal to mu s times Fn, you really can't use this equation for anything in this red region. At this blue dot right here where it is the max, that is where you get to set it equal to, and you actually can use this equation, mu times friction force. And then the last part in green, which is the kinetic friction, that you can use Fk equals mu k times Fn. And you may be wondering then, what do I use for the red region, the static part that's not the maximum? To solve that region, you have to use Newton's second law. In other words, F net equals ma. And that's how you'd find the static friction there. And we'll be looking at more examples of that in the future. But for now, this is everything you need to know as an introduction to friction. So thank you all for watching. I hope you have a great rest of your day, and I'll see you in the next video. Take care, and bye-bye.